Still relying on complex data integrations to track your shipments? You're accepting blind spots, not achieving true visibility. I'm Randy McClure with SC Tech Insights. Custom data mappings invite errors that throw supply chains off track. Today, in this video, I'll show you how computer vision AI delivers picture-perfect visibility instead. Today, we're examining a structural shift in supply chain technology. For supply chain leaders focused on driving long-term return on investment, achieving true operational visibility is the ultimate goal. But let's be objective here. That visibility is consistently blocked by legacy data integration challenges. In this briefing, we'll evaluate how adopting computer vision AI solves these persistent interoperability friction points, allowing your organization to bypass outdated methods and establish a fundamentally sound data architecture. Okay, let's dive into the structure of this briefing. We'll define the core data interoperability problem, examine the computer vision architecture that resolves it, review supply chain node operations, assess how to manage exceptions, and wrap up with a strategic implementation framework. Section 1. The data interoperability problem. Before we can architect a reliable solution, we must first clearly identify the core operational bottleneck present in modern supply chains. If you look at traditional IT methods for setting up shipment status interfaces, they're fundamentally flawed. These legacy integrations are incredibly labor-intensive and slow to deploy, but more critically, they rely entirely on fragile proprietary data mappings. Every time a new partner is added to your network or system updates, these custom data translations create costly friction. It's an outdated approach that actively degrades operational efficiency. The severity of this issue is best captured by this quote from our source material. Complex customized data mappings are prone to errors and ambiguities that throw entire supply chains off track. This inherent fragility is exactly what prevents true end-to-end visibility. When your underlying data translation mechanism is weak, the resulting intelligence is compromised, leading directly to misallocated inventory and delayed response times. Moving to Section 2, Computer Vision Architecture. We'll now transition to the architectural paradigm shift that systematically bypasses this interoperability crisis. This brilliantly illustrates the structural contrast between the two paradigms. On the left, the traditional model requires bulky, error-prone data mappings at every single node. On the right, the computer vision AI solution leverages the inherent understandability of visual data. A simple shipment image, paired with essential contextual data, becomes infinitely more actionable. It fundamentally replaces scattered, localized data translation with centralized interpretation. Let's walk through this engineering architecture step by step. First, local hardware captures raw visual data alongside a tracking ID, timestamp, and GPS coordinates. Rather than attempting to translate this locally, the raw data is transmitted directly to a central hub. There, a cloud-based AI machine learning translator interprets the image into an actionable shipment status, which is then shared with stakeholder systems. The strategic shift here is moving away from complex local data translation to centralized cloud AI interpretation, establishing a true single source of truth. Section 3. Supply Chain Node Operations. Next, we will evaluate the operational proof of this architecture across critical logistical nodes. Now, what's really interesting about this matrix is how it systematically maps hardware deployments to verifiable outcomes at every phase. From imaging towers at the dock, to sensor networks in transit, to augmented reality tools at delivery, the hardware varies, but the objective outcome, undeniable visual status verification, remains constant. Let's examine each of these phases. At the shipping and receiving dock, AI serves as the ultimate safeguard. Solutions like cargo's imaging towers utilize optical character recognition and barcode scanning to process visual data in real time. As a forklift moves a pallet, Persistent instantly validates it against manifests in milliseconds, flagging discrepancies before goods ever enter your inventory. This completely removes the human error of manual scanning. Crucially, these dock cameras aren't translating data locally. They simply capture and transmit. For in-transit events, which have historically been a massive operational blind spot, sensor networks are deployed at critical nodes. Systems such as GenLogs track movement at rail terminals, access gates, and ocean ports where you typically lack direct IT oversight. Local operators simply transmit images and GPS data back to the broader network. This completely eliminates the need to solve complex data integration hurdles at every single third-party transit point. Finally, at the point of delivery, the architecture provides visual proof of on-time arrival at the exact destination. By integrating with solutions like PackageX, drivers equipped with handheld devices, AR glasses, or AI-powered smart lockers capture an image, a timestamp, and a GPS location. This guarantees a highly accurate, undeniably verified proof of delivery, stripping away the ambiguity and potential for error in manual driver inputs. Section 4. Managing exceptions and disruptions. Beyond standard tracking, we must evaluate the application of computer vision AI in proactive risk mitigation. Raw visual data excels at identifying physical anomalies that standard EDI messages simply cannot detect. AI inspection solutions, such as those by Arvest, enable your operations to proactively identify crushed boxes at the receiving dock or instances of container tampering at ports. Furthermore, applying geofencing to visual data generates automatic alerts if a shipment leaves a restricted area. Because the translation is centralized, raw visual anomalies are immediately converted into standardized exception alerts for your management teams. Section 5. Strategic Implementation Framework. We'll conclude with a deployment strategy and the strict technical design constraints required for enterprise execution. Let's see how this builds out in practice. Establishing this framework requires strict adherence to three engineering design constraints, because hardware alone is insufficient. First, every image must be explicitly linked to a unique tracking or load ID. Second, you must mandate standardized metadata embedded with every single image, specifically the ID, a local timestamp, and precise location coordinates. And third, you must deploy a cloud-based AI interpreter. So the crucial point here is centralized efficiency. Deploying processing-heavy computer vision systems at every physical location is a misallocation of capital. Cloud-level AI interpretation centralizes the data translation burden. It instantly converts visual proof from anywhere in the world into status messages that your existing systems can reliably ingest, thereby avoiding the costly integration traps of the past. Which brings us to the strategic decision your organization faces. Will you continue wrestling with fragile, labor-intensive legacy data mappings, accepting ongoing integration friction? Or will you leverage the clear architectural advantages of computer vision AI to build a structurally sound, image-based foundation for long-term visibility ROI? The technology to bypass legacy interoperability is here. The next step is execution. Hello, this is Randy McClure from SC Tech Insights. Thank you for listening. For more on this topic, click the article link below or go to www.sctechinsights.com for the latest insights on supply chain technology. Thank you and see you next time.